Hi guys, my name is Abhishek, and the topic that I've chosen for the video presentation is a multi-tape Turing machine. This is a very interesting topic, and I'm going to give you a definition for it first. So, what do you mean by a multi-tape Turing machine? A multi-tape Turing machine is just another version of our simple Turing machine. The only difference is there are multiple tapes, and each tape is accessed with a separate head and these heads, each head can move independently of the other heads. One thing to note over here is the inputs are only present in the first tape, and all the alphabets are declared as blank in the other tapes. And let's look at the formal definition now. So, a multi-tape Turing machine is a six-tuple machine. So, where Q is set of states, sigma is set of input alphabets, Q naught is initial state, tau is the set of tape alphabets, dou is the transition function, and as you know, F is the final state. For the transition function, we even perform directions for the header. So as I've mentioned it earlier, the headers can either move left or right, they can even be in the same place, that is stationary. So now let's look at a visual representation of how a multi-tape Turing machine is. So as you can see over there, there are two tapes. It's a multiple tape Turing machine, and for the sake of clarity, I'd consider these tapes to be 2D arrays. And also, as we taught in the class, blanks are nothing but deltas over here. In the presentation, I've mentioned the blanks to be deltas, so please don't get confused looking at them. And now, one thing to note over here is these deltas, that is, the blanks grow infinitely to the right side for both of them. And I've mentioned it earlier that the input is only present on the first tape, not on the second. Um, Now let's try to implement them or implement what we've learned through an example. So here we are trying to build a two-tape Turing machine for a palindrome. Consider the string ABA. We are going to check if this particular string is a palindrome or not. This is similar to what we do in programming as well. The strategy we use over here is we copy the inputs of the first tape to the second tape and compare the two tapes. If both the alphabets are equivalent, then that means it is a palindrome. And if it is not, then it is not a palindrome. Uh, I have to explain you how a transition function works over here. So as you can see, xy in the second point, xy, x dash, y dash, d1 and d2. These are a few elements that go into the transition function. So please don't get scared looking at them. X, Y are basically the inputs that are read by the headers of the first and the second tape, respectively. X dash and Y dash are the outputs returned by the headers for the first and second tape, respectively. And D1, D2 are the directions which are performed by the headers on first and second tape, respectively. In D1 and D2 are directions. These can be left, right, or stationary. Just keep that in mind. Now, let's go and have an in-depth understanding of how the Turing machine in the last slide works. So, for the transition of Q0 to Q1, like I've mentioned it earlier, the tapes start with the blank alphabet, that is delta. So, as you can see, delta is skipped and the head moves to the right direction. And for the first tape, and the delta is skipped for the second tape as well and is moved to the right direction. Now let's go. Once we reach Q1 state, here is where the copying takes place. We are not performing any action on the first tape because we're simply doing copying, but there is only change in the second tape. So whatever blank alphabets are there, they are replaced with A's, and we perform write operation on both the tapes. And this goes on for this is similar for input B as well. And like once we reach uh, the end of the string for the first tape, uh, that is when we change the transition from Q1 to Q2. So as you can see, once we've reached the end, we'll be getting a blank. And once we reach the blank, we are performing a left operation on the first tape. And the header for the second tape is going to be stationary. And from Q2 to Q3, we are moving the header of the first to left, and while keeping the second header stationary. So the reason why we are doing this is we are pushing the first header to its first place. Like I've mentioned it earlier, we do the comparison from left to right for the first tape, right? So that's the reason why the header is moved to the left, and once once we reach the front of the first tape, we perform right operation on the first tape and left operation on the second tape. And from the transition from Q3 to the final state happens like this, where we check if both the alphabets are same or not, if they are equivalent or not. And once if all the alphabets are equivalent to each other, then it's bound to happen that we get to see a blank element at the end, that is delta. So once we've reached the blank element, we'll go to the final state, and the headers are going to stay at the same place, so that will be stationary. And that is how the Turing machine would end. And yeah, that's about it, guys. This I've explained you Turing machine with a simple example, and I've given you the formal definition and the definition for Turing machine. Thank you.